All right. So this is the last section of the chapter. So after we did 12.3 with all the partial derivatives, we did the differentials. So I think that's going to be important if you have questions about that today. Chain rule, and then directional derivatives. So all those things are on there. It's quite a lot, but there's some interrelation between these things. So hopefully it won't be too bad. Let me do part of this, and then we'll see if you have questions on. I want to make sure we have enough time. So let's see. So 12.8 is on what are called the extreme values, just like kind of like Calc 1, except so now there's a twist, of course, because it's in 3D. But as usual, I like to make sure you remember it from Calc 1. So the old way of doing this is we would say y equals f of x, and it might be on some interval from a to b. So you have your function, your x values are between a and b, including these things, and you want to figure out where are the high points, where are the low points, the extreme values or the optimal values. So this is like Calc 1. If you wasn't sure what to do in Calc 1, you take the derivative, and then figure out y prime is that, and then set that to be 0. Well, either set that to be 0 or basically where y prime doesn't exist. So you might have some corners or asymptotes or sort of weird points like that. And so then we solve for x in each of those cases, or x. And these were called your critical points. So basically it's, when the derivative is 0, so the graph is flat, the graph might have some weird corners, maybe like absolute value, something like that. It's a critical point, so your 3 areas of critical points in total either came from when the derivative, let's go ahead and just use y because we're using y there, where y prime is 0, where y prime doesn't exist, and also at x equals a and x equals b. So we did have to check the endpoints. And that's kind of important because the function may be, it may be smallest and biggest at the ends, and there may actually be none of these, like a straight line, for example. The derivative is never 0, the derivative always exists, but the min and the max are at the endpoints. So we had to check all of those things if we wanted to figure out that would give us our absolute max and min. Right, so if we really want, like, where's the highest point, where's the lowest point, we check all of these things. Now, if you look at just like the first 2, then these will end up giving us also these relative maxes and mins, or local, relative or local maxes and mins, or maybe neither. So what we had to do is we had to test them. And there were actually two different tests. Let me stick them in here. The first one was called the first derivative test. And that's where you make a sign chart for y prime. I don't know if I'm bringing back bad memories here, but you do a sign chart, and if the sign chart has positive slope and then negative slope, then that means the graph is going up, and then the graph is leveling off. So if my critical point was 0 or even does not exist, if it goes up and then it goes back down, then that meant that you had a maximum at that point. Just can interpret what that means. Y prime is a slope, so it goes up, goes back down. That was the maximum. If you went negative and then positive on the sign chart, It's the opposite. You had a min. So negative slope, 0, and then it goes back up. Now you had two others, which will look like plus 0 and then plus again, or you might have negative 0 and then negative again. Again, these are Y prime charts. In those places, they're not maxes or mins, they're just places where it's flat. So it goes up, levels off, and then keeps going up. Or it comes down, levels off, and keeps going down. So it's not a max or a min, it's just places where it levels off. So that was called the first derivative test. The second derivative test, which actually was easier, but you still had to find the second derivative, is all you needed to do is find the second derivative so the second derivative test, if the first derivative was 0. So this didn't work for the non-existing part, but if the first derivative was 0, so we're testing just the first set of critical points here. You take the second derivative and you just straight up plug in your point. And if it turned out to be positive, so it's 0 is the derivative, so it's flat, but the second derivative, I don't know why I used that, but is positive, that means that it's concave up. Looks like a cup. So in this case, we have a minimum in the original graph. So it has to be concave up, that means it's curved this way, and it has to flatten out because the derivative is 0. So it's those two things put together. If the second derivative is negative, then that means it's concave down. So as they say, concave down looks like a frown, so it's curved down. That actually means it's a max. It's kind of weird, right? It's like, wait, the second derivative is negative, so we have a max? It looks a little different than on the other side, but negative concavity means it's down. The final thing is what happens if the second derivative is also 0 at that point. So the derivative is 0 at that point, the second derivative is 0 at that point. We actually just said, well, that the second derivative test was inconclusive. So that just meant it didn't tell us anything. And so if we wanted to know what was happening there, we'd have to do something else. Maybe go back and do the first derivative, or maybe look at some points on either side of it to see is it going up or down and down, or vice versa. Then, but you couldn't just straight up using the second derivative test here. So that's it. Find the critical points and test them. So that was the old way. Here's the new way, is the same idea. Find the critical points. And then we're going to do a test, then you test them in a second derivative test. And it's going to be called the second partials test. So we won't have that like first derivative test anymore. We're going to be using the second partial derivative test. So we need to know what those are, right? What does it now mean to be a critical point? And then what is the second partial test in order to tell us whether it's a max or a min or possibly neither? So the critical points now, these are going to be x, y points, right? Because we're in 3D where the gradient is the 0 vector. Okay, so what does that mean? That means that this, again, remember, the gradient vector is the vector x derivative, y derivative. So that has to be 0, 0, 0, 0 vector. So that means that simultaneously the first partial derivative for x has to be 0, and the first partial derivative of y has to be 0. And then you solve those simultaneously, system of equations, and that will give you your points where the gradient function is 0. Now, before I tell you what the test is, let's just do some examples where, just for practice, so we can compute these things. So here we go. So for example, let's see, f of x, y equals 2x squared plus 2xy plus y squared plus 2x minus 3. So I don't know exactly what this looks like, but let's just try and find like the hills and the valleys, just like we did in Calc 1, except now it's like truly a topographic hill and valley kind of thing. So we need to figure out where those are. And so we need to find the critical points. And that just comes from simultaneously finding f sub x and finding f sub y and set them to 0 and solve that system of equations out. So how do you do that? Well, let's see. So f of x, partial derivative here. So I get 4x from that one. This one, y I think is constant, so that's 2y. And then I get 0 because y squared is constant, and then plus 2. And then fy, the 3 is 0, of course. If I do fy, then I get 0, 2x, 2y, and that's it. So there's my system of there's my partials. So now what I need to do is I need to set both of those to 0 and solve that system of equations. So what values of x and y will cause that to be 0? So hopefully you can do that one. Math 103, or just, substitute or multiply the top equation by -1 and then add it to the bottom one, or even just reason it. Look at this bottom equation. Well, if 2x and 2y add to be 0, then that certainly means that x has to be the negative of y. So if I took that and substituted it into the top, I think you can pretty quickly get that y is going to have to be 1. Yeah, so sub in, you can figure out that y has to be 1, and therefore x and y are opposite signs, so we get x equals -1. So that means that the critical point is just when x is -1 and y is 1. Now, if I wanted to get the full point, like what point on the graph, then I'm going to have to figure out what the z value is. So this is something we kind of glaze over even in Calc 1. We just find the x's. And we're like, hey, the maximum is there. Well, okay, but what is the y value? Yeah, we could plug it in. So let's just do that here to make sure we get the full thing. So that means the actual point we're interested in is -1 for x, 1 for y. But then what's z? Well, z is just the function value when I plug in 1 and 1. So just like normal, you plug in the points to get y previously, now you plug in to get z. So you plug in, sorry, this is -1 and 1. All right. So I plug in -1, I get 2 minus 2 plus 1 minus 2 minus 3. So wait, what was that again? It was 2 minus 2, so that cancels 1 minus 2 minus 3, so -4. So whatever this graph looks like, it does at least pass through the point -1, 1, and -4. And that is a critical point. But the question is what kind of critical point is it? So is it a maximum? Is it a minimum? Is it something else? Is it like a flat point? Is it something questionable that I haven't seen yet for 3D? So we need to figure out how to test that. So keep this picture in mind, and we will test it and tell you, is this a peak, like a hill, or is it a valley, or does it just happen to be a place that levels off? So suspense will rise. We'll keep that in mind. But before I do that, let's do another one. So z equals x squared, or y squared minus x squared. So it's actually even a smaller one, but testing it will give us something interesting here. So we can plot this. In fact, you can do this. You should be able to do this, where you set, you do your traces. We set x to be 0, we'll get a parabola. We set y to be 0, we get a parabola. We set z to be 0, we get lines, or if we set z to be 1 or -1, we get hyperbolas. You should be able to piece all these things together now in your little topo map. But anyway, if we just straight up did the x derivative and the y derivative and set them equal to 0, then the x derivative is just -2x. The y derivative is 2y. If I set fx equals 0 and fy equals 0, this is a pretty easy one. The only way that works is if x is 0 and y is 0. So I get x equals 0 and y equals 0. And so my true point here is 0, 0, and then plug it back in to get z, 0. So there's my critical point there. It's just 0, 0, 0. And so then, is this a max? Is this a min? Which one is it? I'm not sure I've done the full topo map, so this is, I mean, it's good practice maybe anyway. So let's just try for different values of z. So let's just look at level curves for z. So if z is 0, then I will get 0 equals y squared minus x squared. So to bring the x squared over and take the square root, I'll get plus or minus y. So I'm not going to go through all the steps here on this because it's going to get too cluttered. But level z equals 0 has these two lines as my level curve. If I set z equal to 1, then I'll get 1 equals y squared minus x squared. And that's a hyperbola opening. So there's x, there's y. It's going to look like this. And those level curves will both be when z is 1. So both of those are going to be 1 unit up. If I did z equals -1, then I'll get -1 equals x squared minus y squared, which if I reverse all the signs, that'll be 1 equals x squared minus y squared. That's also a hyperbola. So that one's a hyperbola, that one's a hyperbola. But this one is now over here. And so that's when z is -1. And this is also when z is -1. And if you plot more and more of these different values for z, you're just getting hyperbolas and hyperbolas all over the place, whether they're up out of the board or they're down into the board, depending on which side you're on. All the negative ones will be opening left, right. All the positive ones will be opening top, bottom. And so that's at least what the topo map looks like. And we can then piece them back together when I draw the eventual picture here. So that's it. You take the critical points and by finding where each partial derivative is 0. So now how do you test these critical points? And this is called the second partials test, and it actually uses something called the Jacobian, which you may see in Math 301 if you end up taking Math 301. Second partial test. You have to do this. So what you do is you define, and I think the book uses, they use a shouldn't be using capital D, but we're going to do it anyway. So we define capital D, which is called, the discriminant. Let me leave that off for right now. And what it is you take the second partial derivative with respect to x, you multiply that by the second partial derivative with respect to y, and you subtract off the square of the mixed second partial derivative. And then you evaluate this, and then evaluate it at each critical point. And you'll get a number. So D will look like a function, but then because you're going to have all these x's and y's in it. But then you evaluate it at each of the critical points, and you look at what that number is. And there's going to be four cases here that will tell you whether it's max or min or maybe something else. So number one is if the D value ends up being a positive number. So if you take your critical point, you plug it into this function, calculated it out, if this turns out to be a positive number, then one of two things could happen. You also have to compute, and you also have to compute the second partial derivative for x at that point as well. And if that ends up being positive, then the function has a relative minimum. And this one's, why the D even comes into play is tricky, but you start thinking about this as kind of like a concavity, right? It's a second derivative. If it's greater than 0, then that means it's curved that direction, like our smiley face, our cup. Therefore, minimum makes sense because it's curving this way, and so that bottom point at the bottom does look like a min. Similarly, if this discriminant is positive and the second derivative with respect to x, when you plug in the critical point, ends up being negative, then that's kind of like negative concavity you can think of, and therefore it's f has the relative maximum. Okay, 3, if D is negative, we're going to get something in case 4, which I'll just give you this right now. If D also ends up being 0. So the critical point, again, came from the fact that everything was 0, both partial derivatives was 0, and also you plug it in and this ends up being 0. And the test is what's called inconclusive, just like we had before. So that sort of stinks. Second partial derivative didn't work before. When we had 0 and 0 again, we had to use something else. The same thing holds here for the fourth case. So 0 and ends up being 0. If the second, if partials, this discriminant ends up being a negative number, then f has a flat point. It's not a min and it's not a max. So it's a different kind of flat point. And this is called a saddle point. As a saddle point. It kind of looks like a min from one direction because it's leveling off, but it also looks like a max from the other direction. So this is called a saddle point. And so we'll just do the picture on that one. And that's exactly what we have in this one here. So I don't know if you can see it from the topo map, but it's like, you know, these things are coming up along this parabola here. So they're coming up the hyperbolas until they hit these cross lines. And then they switch over and they keep going up on this side. So it's kind of like they're curving this way, but on the other side, they're curving down. That's really helpful moving this in 2D here. But if I did plot that again, right? So if I looked at the plot of z equals, which direction is that? Y squared, yeah, y squared minus x squared. It looks like a parabola one direction. So it looks kind of like a min, but it looks like another parabola in the other direction. And then you have all these hyperbolas in here. So it's like this on one side. It looks like, and I'm used to drawing it. I'm used to drawing it the other direction just because it's hard to do that. So I won't put the axes in there, but it kind of looks like a min the one direction. It looks like a max in another direction. And it looks like parabolas, hyperbolas, sorry, this one. So this is also the Pringle chip idea. So it does hopefully now look kind of like a saddle. So if you're coming in from this direction, it looks like I'm going up to a maximum, this flat point. But at the same time, it also looks like a minimum on this side. And so this is called a saddle point. So let's verify that that actually works with my second partials test. So If I went back and just tried to use it, then again, let's see. So I take the fx and I get minus 2x. I took fy and I get 2y. And again, I take these things, I set them equal to 0. And I got my critical point where x is 0 and y is 0. And of course, z is 0. So now let's do the second partials test on it. So I need d, which was the second derivative, second partial for x times the second partial for y. And then I subtract off the mixed one, squared. Okay, so what is the second partial derivative with respect to x? That one's going to be do an x derivative, then do another x derivative. That'll be -2. There's actually no x's in it at all. What's the second partial derivative with respect to y? So that means do the y derivative and then do the y derivative again. So I've got my y derivative as 2y. I do the y derivative again and I get 2. If I do the mixed one, that means do x first. So I get minus 2x, but then I do a y derivative of that. So if there's no y's, and there isn't any, that's going to be 0. So my d ends up just being -4. So d is less than 0. So I go back to my second partials test. I go through the cases. D is less than 0. Therefore, f has a saddle point. So it has a saddle point at 0, 0, 0. Which, of course, is now no duh, because I already drew it. So if you can draw it, then you probably can just look at the answer and know what it is. I don't want to have to draw the picture every time, because sometimes the pictures are bad. This happened to be a pretty nice one. So if I go back to even the first example that I had, back to the first example, that was f equals 2x squared plus 2xy plus y squared plus 2x minus 3. Let's find all the derivatives here, because I'm going to need all of them. So I did the x derivative, that's 4x and 2y and 2. The y derivative is 2x plus 2y. Now I want to do my mixed, or my second partials, including the mixed one. So I do xy on these. And my fx and then x will be 4. My fx and then y will be 2. So that's like xx. Here is xy. If I did yx, I also get 2. That's sort of a verification that those are equal, which they always are for our cases. And then I do yy, which is 2. So that's yy. So that means that d is the fxx, so that's 4, times fyy, which is 2, minus fxy squared. So that's minus 2 squared. I'm just plugging in those things. Again, I don't have any x's or y's, so I don't have to worry about where I'm going to plug in my critical point, which again, let's see, the critical point was -1, 1, -4. You're going to have some examples where you have like x cubes and higher powers, so that when you do these, the d will end up having places where you have to substitute in x and y to make it work out. But in this case, I get 8 minus 4, which is 4. So that means that d is positive. Okay, so if d is positive, I go back to my partial test and I look. Now I have 2 possible cases where d is positive. So if d is positive, you have to shift and go back and look at the xx derivative and determine whether it's positive or negative. So you have to check both things. So if xx is positive, then you get a relative min at that point, and if xx is negative, you get a relative max. let's look at fxx. And in this particular case, my fxx is 4, which is also positive. So you put those two things together there, the d is positive and the fxx is positive, so you get a relative min at -1, 1, -4 by the second partial test. So it is pretty straightforward. Find the critical points by taking the derivatives, plugging them in, and then checking the second partial test to see which ones they are. And I think actually that's probably going to be the best place to stop, because otherwise it's going to be quite a lot, and I want to make sure that you have time to get questions in. To conclude this next time, and I think the homework's not due for a little while anyway. The question is what is the equivalent to, you see, back in the very beginning, we said the critical points were at where the derivative was 0, where the derivative didn't exist, and then the endpoints. So the endpoints is the trick here. So in 3D, what is equivalent to the endpoints in 3D? And that's a question will be answered tomorrow. We're not going to do that today. But these are something called, instead of just straight up optimization, it's called constrained optimization. So instead of letting X and Y be anything they want, you now impose some endpoints or whatever that means, and then look at it so we can find global maxes and mins instead of relative or local maxes and mins. Kind of like the real world, where you might have something that's like, all right, here's a metal plate, and you have a burner on it, and it's heating up, and you get some sort of temperature on it. It looks like a piece of toast, and now I'm hungry. What is the temperature distribution on this plate look like? Where is the cold and hot places inside the plate? And then the question is how about on the edge? Are the cold and the hot places of a metal plate on the edge naturally? Or are they in the middle? Or is the edge like dissipate out? Or, I mean, how does that actually work? So instead of thinking of this F as just F, I think that for those, you're going to think about this as like a temperature. Where is the highest temperature? Where's the lowest temperature? Does it occur at just one point? Does it occur at multiple points? And so we'll impose some sort of like external end point. I don't want to use the word yet. We'll do it tomorrow. All right. Just for my voice sanity and my sanity and my voice break here, just take a quick another like 5-minute break. We'll come back at 8:55, and then that'll give us a little over half an hour to see if you have questions on homework or things to get caught up or concepts. Again, a lot of you are not turning in anything, and you're shooting yourself in the foot, because yeah, the grade will suffer, and then I think tomorrow the test will seem like form if you haven't worked on these problems. So, all right, 8:55. See you back here then.